So the Perspective on Science and Math course is essentially a history course. It's a history course for people who are math and science majors. So we look at a selection of episodes in mathematics, biology, physics, astronomy, chemistry. We try to cover topics that will connect to issues that might actually show up in the high school classroom. One reason why I think this course is valuable to students that will become teachers is that it'll show them many of things, the sides of science and mathematics that are normally hidden. They're not hidden because they're bad or because they're ugly. They're actually quite interesting and they're actually quite useful. But they're hidden because teachers, mathematicians, scientists, they just don't have a lot of time. So they'll be more focused on teaching students the results than the process, teaching students our current doctrine than the history of how we got to that. But it's encouraging when you find out the way in which people in the past have made false starts or made big mistakes or come up with interesting hypotheses that fell by the wayside. It's interesting when you look at that because then you get a better sense of science in the making and a better sense that the people who are making the science and the mathematics were kind of like ourselves. So my original idea for today's lesson was that statistics and probabilities are an interesting topic in which mathematics, science, and games converge. And I thought, it should be appropriate that since these topics overlap so many realms of our experience, that it'd be nice to have a history of science class which is kind of about that. I knew about this three-door problem from years ago, and many people know about this problem. It's now routinely taught in probability classes, but it wasn't always taught. Part of what's missed by just teaching the straightforward, say, a Bayesian analysis or just some simple mathematical way of breaking down the solution to the problem is that students won't realize the drama and the extent to which people have fought over something like this. So I wanted this class to get the students to see the problem instantiated in this Monty Hall situation, make up their own minds before I tell them what Marilyn Vos-Savant said about it, then have what she said, then what specialists said, then have the experiment, so that we can kind of go through a journey in which you can kind of see how our knowledge depends on our information, or how people's disagreements can actually be played out. I want people to actually go through a phase in which they formulate their decision, and after they've formulated it, they actually get to experience the difficulty of having to change it. How can it be there's two doors? How can it be that I don't have a 50-50 chance? Why is the world against me? I want to hold on to my decisions. That's what I want to capture. Now today I want to talk about a similar topic as to how do some conventions enter mathematics? How do mathematics and conventions interrelate? National Safety Council estimates, based on data from the National Center for Health Statistics and from the US Census Bureau, came up with the following figures in 1999. The odds of dying because you were bitten or struck by a dog are 1 in 142,000. Cute little puppy, right? The odds of dying because you were bitten or stung by a non-venomous insect or other arthropod like a spider, a non-venomous one. The odds of dying there are 1 in 355,000. The odds of dying because you were hit by lightning, 1 in 55,000. Accidental suffocation and strangulation in bed. Strangle yourself with your shirt while you were half asleep, your pillow. The chances are 1 in 10,000 that you will die. From the moment you're born to the moment you die, there's a 1 in 10,000 chance that you will die from strangulation, accidental suffocation on your bed. Well, these numbers are in general. To find whether they're odds that apply to you would be a more complicated thing. But moving along, the chance of dying from a fall involving your bed, a chair, or other furniture is 1 in 5,700. The chance of dying in an uncontrolled fire, 1 in 1,300. The odds of dying in a car, 1 in 244. Next time you're in a car, think about how dangerous that is. Now, once we've done these analyses, these statistical analysis of regularity, then we can come up with some sort of study of probability. Well, what are the odds that something will actually happen to you? Well, one guy who analyzed this problem in the 1600s, one of the pioneers in this field, was Blaise Pascal. Now, Blaise Pascal is a really talented kid. He loves mathematics. His dad says, look, this is a waste of time. You shouldn't do this until you're 15. First, you got to learn your languages and stuff. Finds his kid actually with a piece of charcoal writing some geometrical proof on the wall and says, okay, fine, you can study mathematics. And this kid feels bad that his dad is so busy all the time, exhausted, making difficult calculations on tax tables. Endless calculations. The French monetary system at the time was pretty complicated. So Pascal devises a little mechanical computational machine. It's now called a Pascaline. It's one of the first calculators. You can use this to actually do certain arithmetical operations, which was difficult at the time because, as I said, the monetary system had certain weird ratios. They make about 50 of these. They don't become a financial success. But the neat thing that they were too expensive to manufacture, the neat thing about this machine and about Pascal's involvement in this for our purposes, it brought to light the possibility of, can we, since mathematics is one of the things that distinguishes us from animals and rocks, can we make a machine that will think? Or in another way, can we make a mathematical algorithm, a set of processes, ink steps on paper, that will replicate something like the way in which we make decisions, the way in which we come to one judgment or another? Now, Pascal becomes interested in probability because he has a friend who's a gambler. And the gambler gives him the following question. Before I get to that, let me give you one of the basic principles of the time. If we say, well, you have two six-sided die, you roll one die, there are 6 possible faces that might show up. So there are 6 possibilities. How many possibilities have you rolled 2 dice?
36.
How much, Kelly?
36.
Why?
Because it's 6 squared. 6 times 6.
Why is it 6 squared? Why not 6 cubed?
Because you're only rolling 2 dice. Because there's 6 possibilities for each one.
Okay, so say 1, 2, 3, 4, 5, 6. Your die can show any of these. And once it's shown one possibility, the other die can also show a series of numbers, like 1, 2, 3, 4. And then once you've got this, you can have 1, 6, or 2, 6, or 3, 6. You complete this grid, you're going to get 6 by 6, and thus the square that Kelly was talking about. And we say, look, for any kind of a different random generating process, we can do a similar kind of multiplication. This becomes known as the multiplication principle. This is already known in Pascal's time. The reason I bring it up is because he's going to use it. But I was saying, in the summer of 1654, he analyzes a problem posed to him by a friend who's a gambler. And the problem is this. 2 people have been playing a game flipping coins. You're flipping coins, and they say, well, look, whoever gets 6 guesses right first wins all the money. Maybe there's 100 coins. Maybe Rudy says heads all the time, and I say tails. We start flipping. Whoever gets 6 heads or 6 tails first wins all the money. But the case that Pascal is interested in is an interrupted game. We're looking for 6 faces or 6 tails, and instead, I win 5 times, and then Rudy wins 3 times. And maybe Rudy's wife calls him and tells him to stop wasting his time and his money, calls him inside and forbids him from ever playing with me again. So this is an interrupted game. Because neither of us reach 6, the question is, who should get the money or how much of it? Ideas?
You should get the money?
Yeah, who should get the money? I should get all of it.
Well, you were closer.
Teaching assistants are so helpful. So yeah, so I should get 100%. That's one possibility because I was closer. How do you feel about that? What would you like? We can't play again. You moved to France. You're gone. We can't flip that last coin. So what's going to happen? Who Who should get what? 50-50. So I should get 50%. What else? Paul? Proportions?
The percentage. Like we should get a 3/8.
So what he's saying is we rolled the die 8 times. One guy won 3 times. I won 5 times. So I should get 5/8 of the money. The other guy should get 3/8. Is that good? Is that what we should do? Well, Pascal argues as follows. He says, look, if we could continue playing the game, we flip the coin one more time. Rudy has a half chance of getting that coin flip. He still hasn't won. We flip it again. He has a half chance of getting that. We flip it again. He has a half chance of getting that. What are the odds that those 3, which is given by the multiplication principle? So the odds that if we keep playing, he will win. He has to win 3 in a row. And the odds of that are 1/8. So Pascal says he should take 1/8 of the money and I should take 7/8. Because he formulates that argument, many mathematicians become increasingly interested in this question of statistics. In this question of probability. What's significant here, the reason I bring you this particular example is because this 1/8 or 7/8 and 50% or 100% are not decided mathematically. We use the mathematics, but we're not bound by it. Well, in 1950, a couple of employees at the RAND Corporation, RAND just stands for Research and Development, a couple of employees there, Merrill Flood and Melvin Drescher, they come up with an interesting mathematical game. And that interesting mathematical game is quickly seized by a friend of them. Drescher tells Tucker. Tucker is a mathematician at Princeton, and he sees that this game has a bearing for something about the psychology of human decisions. So he presents this game in a revised format to a group of psychologists at Stanford University that same year in 1950, in May of 1950. And he calls it the prisoner's dilemma. The prisoner's dilemma is the following. I need 2 criminals. Okay, we got 2 criminals. We got Mark and we got Jesse. 2 criminals, you've both been arrested. We caught you red-handed for a minor crime. You are both going to jail. Both of you are going to jail. But we're going to cut you a break. Jesse, if you confess that he did it, you go free, and he gets 10 years.
My lawyer, bro?
Your lawyer is not present. It's just you and nobody else. You can't even see, that's you. You can't even see, you cannot communicate with Mark. You know only one thing about Mark, and that is you met him in jail, and he is a criminal. That's all you know. Now, if none of you say anything, you both go to jail for 3 years. If both of you rat on the other, you both go to jail for 5 years. But if you rat on him and he doesn't rat on you, he goes to jail for 10 years, you go free, and vice versa. So what would you do?
I stay quiet.
You stay quiet. And you?
Stay quiet.
Now you both go to jail for 3 years. Now Tucker presents this kind of argument to the psychologists. He says, look, here, if prisoner A confesses, he goes free. If you stay quiet, you go to jail for 3 years. So what would you choose? Go free or go to jail? I'll choose go free. Now, if you confess and the other guy confesses, then you both get 5 years.
Friend or foe?
Now, I'm sorry? Say again?
There is a game show that uses this thing. It's called Friend or Foe.
Friend or foe.
You split the money when you go to the podium and they say, okay, it's split the $100.
So,
they both choose foe, nobody gets anything.
Yeah.
They both choose friend, you get 50.
Yeah.
And if you choose foe and the other one chooses friend, the foe takes the money.
But what I want you to try to see here is the way Tucker sees it. Now, naturally, they're sitting next to each other. It's a funny, friendly environment. It's not a real life or death situation. 10 years in prison is not on the line here. So they say, yeah, I'll confess, you know, whatever. I mean, I'll be quiet. I'll be true to my friend. But when you analyze this rationally, what Tucker concludes is that logic prevents you from cooperating because the risk of cooperating is too big. If you assume that the other person will stay quiet, like you will, then you're risking 10 years in jail. 10 years in jail. That risk is too big. So he claims it is rational to cheat and betray. That's the rational solution mathematically. So we have a strange little game, a strange little situation in which a particular decision is prevented because of the way, a particular cooperation that we could do is prevented because of the way we analyze it. This had many applications for the analysis of social dilemmas. So how do we make choices? How should we mathematically? At about the same time, in the 1950s, a little girl is growing up in Missouri, St. Louis, Missouri. It's related to the famous philosopher, physicist Ernst Mach. Her name is Marilyn Mach. And the point is, this little girl is pretty smart, so she takes an IQ test. The IQ test, after you've answered all the questions, it gives you a number for what is supposedly your intellectual age. And then you divide that number by your chronological age, your actual age. She's 10 years old. You multiply that by 10, and you get a number, your IQ. Someone who's 150 IQ is said to be really, really smart. 100 is average. You are as smart as your age. Her score was 228. So she becomes entered in the Guinness Book of World Records as the smartest person alive. So what does a little genius do? She becomes a writer for a magazine called Parade, where she answers people's obnoxious questions. And she takes her mother's last name because she believes that people should have, you know, daughters should have their mother's name and sons should have their father's name. At any rate, she receives a letter in September 9 of 1990. She also married that obnoxious guy, Robert Jarvik, who invented the artificial heart, who tries to sell you Lipitor on TV. She gets a letter in 1990, and the letter says this: Dear Marilyn, suppose you're on a game show, and you're given the choice of 3 doors. Behind one door is a car, behind the other, goats. You choose a door, say number 1, and the host, who knows what's behind the doors, opens another door, number 3, and shows you, here's a goat. I knew here was a goat. And he says, do you want to switch? Do you want to keep your original door, or do you want to change to the other one? So the question is it to your advantage to switch the choice of doors? Is it to your advantage? Now, Lauren's going to pass around a sheet of paper. I want you each to answer. Should you switch, or should you stick? What are the chances? The question is, what are the chances that the car is behind your door? Is it 50% chance that it's behind your door? Is it 10% chance? What are the chances that the car is behind your door? Quickly, we want your feedback rather than your neighbor's feedback. So, okay, so the question is this. As the instructions say, there are 3 doors, you pick a door, and after you pick the door, which might have a car, then you are shown a door that doesn't have a car. And now the host says, do you want to keep your door, or do you want to change to the other door? But the only thing the question is asking you is, what are the chances that your door has the right thing when there are only 2 doors left? There are only 2 doors left. There's 1 car. It's behind one of them. What are the chances that the car is behind your door? All right. In the 1960s and 70s, there was a game show called Let's Make a Deal. It was hosted by a guy called Monty Hall, a car salesman kind of guy.
I have a deal for you that is fantastic, and I don't think it can be beat, because it's right back of that curtain, and this is what you may own in the next few months. It is America's newest sports car.
And that's the Brooklyn with safety has the most important design factor, dramatic styling, luxurious interior, and the unique all-wing doors for both safety and convenience. Brooklyn, the car of tomorrow, today. From Brooklyn Vehicle Corporation, that retails for $7,695, and we're adding tax and license for a total of $8,920.70.
That automobile, which is the latest, newest sports car on the market, worth $9,000, the way we're going to give it to you, if you win it. We'll put you in a very exclusive company because there are no more than 500 people in the world that own one of those. And it may...
So yeah, there's one car, 1974 Brooklyn, that you always want. It's behind one door. There are only two doors. It's a beautiful yellow car, and the doors open upwards. You can get as fat as you want. You always fit in. So let's see, Lauren. Let's see the answers. Let's see, Samantha Marion says there's 33% chance that it's behind your door. Where is she? Sam, why is there 33% chance? There's only two doors. You're saying that there's only a third of a chance that it's behind yours.
I'm not really sure if I'm right about the percent. I know it's less than 50. If you have 3 doors originally, there's 33% for each. But then they take away one door, and I think that there's 66% on the other door, and then 33 on the original door that you picked.
Son, you said there's 50% chance. Why?
Well, there's only 2 doors left, and you know you're probably in one of them. The other one goes in it. Out of the 2 asking.
Jason, you said 50%.
Yeah, I'd like to change mine. I like the Sanders estimation.
Okay. What about you, Ann? Are you going to change yours?
Yeah.
Well, Marilyn Voss-Savant gave an answer. She said you should switch. There's 2/3 of a chance that the car is behind the door that you did not pick originally. Letters start to arrive at Parade magazine. Professor of Mathematics, Florida State University, you have shown a misunderstanding of the rudiments of probability theory and an appalling lack of logic. The answer is 50-50. Another professor from University of Florida, you blew it, and you blew it big. Shame. Her editor writes to her, we have a problem. They receive letters from prestigious universities, from the National Institutes of Health, the Department of Justice, the CIA, the FBI, the U.S. Army Research Institute, the Deputy Director for the Center for the Defense Information, and even from pilots from the Persian Gulf. People write, your answer is clearly at odds with the truth. May I suggest you obtain a standard textbook on probability? A mathematician tells a reporter about her complete gross stupidity, her stubborn refusal to acknowledge that the odds are 50-50. She writes an article saying the odds are 2/3. People continue to write letters. I am in shock that after being corrected by at least 3 mathematicians, you still do not see your mistake. Another PhD, you are utterly incorrect about the game show question, how many irate, angry mathematicians are needed to get you to change your mind? Dear Marilyn, as an educator, I find your column reprehensible and urge you to reconsider your future endeavors. In my opinion, you no longer provide a useful service to your readers. I would encourage your publisher to print a strong apology to the 3 scholars whose wisdom you rejected by your illogical babble. I hope they sue you. Sexism enters the game. Your answer, a professor from the Department of Pure Mathematics at Cambridge University writes to her, your answer is incorrect. I wager your womanhood is a factor. Another person writes, maybe another guy from Oregon, maybe women look at math problems differently than men. And another guy says, Marilyn, you are the GOAT. So Marilyn does an experiment, answering the question verbally as Sam did or as you guys did, Son. It doesn't solve anything. So she says, look, I want kids in schools throughout the country to carry out the following experiment. I want you each to do a game in which you choose from three doors. You choose. There's a die in your set. The cups are numbered. What you will do is I'll tell one of you to turn around. Jason, turn around. I'll roll the die. I get 2, so I put it under cup number 2. Now I ask him to choose. Come back, Jason. Choose one. He chooses number 1. I show him that 3 doesn't have it, because I remember where it is. Now I give him a chance to switch. Do you want to stick with your choice or do you want to switch?
I'll switch.
He switches because he heard that in this case it's behind number 2. Once the person has switched, pass these around, pass one per table. Once the person has switched, then I want you to, or has stayed, I want you to choose the column stick or switch, stay or switch, and in that column write win or lose. Start. Write them on the form. And we're going to see what numbers we actually get. Choose one person in your table that will play the game.
Sweet. Okay, so you switched. Okay, I'm turning around.
I think he wants to turn around.
Okay.
You gotta get him to turn around.
Switch.
Nope.
Don't give me hints with your facial.
Oh, they actually are numbered.
Yeah, they are numbered. So, okay, so I guess turn around and. All right. Pick one. All right. No deal. Okay. Yeah, it was in there. You're right. This is funny. Okay. No, your team is turn around. Everybody keeps guessing where I put it. Oh, okay. All right, go ahead. Turn around. Okay. So how would we?
All right, you have 1 more minute. Try to get as many results as you can. You have 1 minute.
2/3. Which one?
Three?
Go.
Alright. Oh, okay.
Yeah. Go.
All right, time is up. Time is up. I'm going to go table by table, see the results. All right, Anne. All right, here. And in their table, they switched every time. They got 7 out of 13 wins. Here, what did you guys do? What was better, to switch or to win in the 5 trials you had?
I lost every time I stayed.
In your, she won 3 times and she lost a couple of times. Something like that. Here, switch or win or change. What worked?
Switch.
Switch, you won once. Stay, you lost every time. Here.
Here,
2 out of 5 times.
So switching worked a little bit better. But you did try it more.
Well, we only stayed.
Yeah, you only tried a few samples. But
We only switched a couple times, but we won both times.
so that both times that you switched, you won and you lost a few of the others. And here,
We always
You-
switched and he won 5 out of 8.
so Maryland receives hundreds of letters from different schools and even universities around the country where people have performed this experiment. 50,000 students across the country contributed to getting the results that then she tallies, and she says, look, 66.7% of the time you win by switching. Now, this analysis had been published already. She had shown this in print, and people, PhD mathematicians, had still not been convinced. So it wasn't the rule that convinced them, it was the experiment. If you choose door number 1, the car happens to be behind door number 1, and you switch, you lose. If you choose door number 1 and the car happens to be behind door number 1, happens to be behind door number 2 and you switch, you win. And it happened to be behind door number 3 and you switch, you win also. So the point is, you can see by drawing a chart that it is to your advantage to switch. But the difficult thing conceptually is why? Why is it that the missing door, the door that hasn't been opened or looked at, somehow pairs up with the door that was eliminated by the host rather than with your door? There are 2/3 of a chance that your door and door number 2 are right. There are 2/3 of a chance that your door and the other door are right. So why is it that there's still only 1/3 on your door? Your door has 1/3 and the door you didn't choose, the door you always never chose, has 2/3. Why is that?
Because they will always remove the door that does not have prize. Right? The host will.
The host will always remove a door that does not have the prize, yes. Mark?
So when they remove that door, it doesn't change the probability because you still get 2/3 of a chance that you did not choose the correct door.
Yes, I like that kind of answer for the following reason. There are 3 choices and you chose one, so there is 1/3 of a chance that this is right and there's 2/3. And now whether or not the host shows you a goat back here, whether or not he shows you a goat, if he gives you a chance to switch to this set, you should. But even whatever simple explanation you try to do, whatever one-liner is not sufficient, many people will still not be convinced, and you in your bones might not be convinced. So the experiment became a subject of analysis for researchers. A guy at the University of Missouri, Donald Granberg, I'm trying to write his name. Does a series of social experiments. He does experiments to see whether people switch, why they switch, when they switch. He finds that giving the actual experiment with doors to students, 174 out of 190 students, 90% of them decided not to switch. 174. Why? Because they think it's 50-50. But still, a gross majority, 90% decided not to switch. People who were giving the quiz on paper, 228 students that he gave the quiz, only 13% of them switched. Again, the majority did not switch. So he finds, look, people tend to stick with their initial hunch. And the question is why? He thinks, well, maybe the human brain is not wired to analyze this, because this is a rational situation in which it's to your best advantage to switch, but you don't, even when you think it's 50-50. If it's 50-50, you might as well switch. Why don't you? Because people identify with their choice. People want to hold on to it somehow. So the key point of Granberg's research is that even when there is no rational basis for staying with your choice, people stay. And by asking questionnaires to people who make that decision to stay, he finds that one of the factors is how people will feel if they lose. If you switch and then you lose, you will feel much worse than if you stick with your guts and lose, because at least you didn't have it and then give it up. People say that people will be frustrated and angry, more frustrated and angry if they change their original choice, their one-time choice. You only get a shot at the Bricklin once and you get it wrong. So more generally, this seemed to fall under the psychological topic that by then, since 1985, had been known of belief perseverance. People tend to stick to their original belief, their hunch. Whatever they originally set their mind on, it's really difficult to get them to change even after you've laid down an argument for them. There's also another psychological issue here, which is the illusion of control. You're like, no, I have it. I'm going to stay where I am. I'm not going to move. It's risky to change. Now, this problem that gave Maryland so much fame in the 1990s has a striking resemblance to a problem that had been formulated decades earlier and published in 1959 by a writer called Martin Gardner, who never even studied mathematics. One of the most prolific writers in recreational mathematics in the world, and one of the great defenders of rationality that is left alive, that is, if he is alive, because his birthday was yesterday. October 21st, he became 94 years old. That means that now there might be a 46% chance that he will die within the next 3 months. At least he's not at Salt Lake City, Utah. Now the problem that he formulates is the following. 3 men, different set of doors. 3 men have been put in jail. You're all in jail and you're all going to die. But the governor changes his mind, decides to forgive one of you. He rolls the die, one of you is going to go free. He tells the warden, you find out that the warden is going to set one of you free, so you ask him, is it going to be me? The warden says, I can't tell you that. So you say, well, can you tell me if it's going to be one of the other guys? The guy says, I don't know, I'll think about it. The warden comes back the next day and he says, son's going to die. He tells you that, son's going to die. And now he walks away and you smile and you laugh at him. The thing says, you say, I can't believe the warden's gross stupidity. By telling me that son's going to die, now I have a 50% chance of living. Yesterday I had 1 in 3. Now there's only 2 of us, so my chances have gone up. by 20%, which is just wonderful. I have a 50% chance of living. The question is it the same problem? Do I have 1/3 of a chance of living, or do I have 50%? What do you think? Gardner got a lot of letters over this.
The person was chosen the first day, right?
The person was chosen originally. Then the warden decided to forgive I'm sorry. Yeah, he decided who to forgive that first day, and nothing has changed. Nothing has changed. You cannot switch. Are the chances that you will die, are they bigger than the chances that your neighbor will die, or are they equal? They're equal, you say? Anyone else? Equal. Gardner says you're wrong, and every mathematician say you're wrong. They say it's the same situation as the Monty Hall problem. Now this is the eerie situation. Suppose you're not in jail and you're just in a mental institution, and every night somebody gets electroshock. 2 out of 3 people, we can't electroshock everyone because electricity is too expensive. And to make it interesting, we roll the die. We roll the die. And you always tell the warden, is it going to be me? And he always tells you, no, I can't tell you that. So he tells you the name of the other person. Eventually, you realize that your odds are still night after night after night after night after night after night, 1/3 of, only 1/3 of not getting the electroshock. So one day you ask him again at night, who's it going to be? Is it going to be me or him or the other guy? And when he's about to tell you, you say, wait, don't tell me, tell the other guy. So that, because the question is, why is it what is so special about my knowing? Son doesn't know that he's going to die. So now because I know that he's going to die or that he's going to get electroshock, now somebody else, maybe Shanna, has a bigger chance of not getting it because I know. So now I say, well, don't tell me, tell one of the other two. So what I want you to take home from this is that even if you walked into this class knowing that the Maryland question is 2/3 and that you should always switch, there are many other puzzles that are similar and equally complex, and they're not necessarily give the same answer. Now Gardner says it does give the same answer, but the puzzle in your mind is to understand why. Another puzzle that I want you to think of when you're watching TV is that new TV show, Deal or No Deal. There were many cases, you chose one, then you eliminated all of them until there's only 2 left. Now should you switch, or is it just 50-50? So you think. Think about it and you might change your mind.
Yeah, so this is actually my favorite UTeach course so far, and I think that the way that Dr. Martinez runs it is just fantastic. He just from the simple organization of it, he always has whatever the hook is and everything like that, which I know is something they try to encourage but don't always follow in the other UTeach programs. But he actually pulls it off pretty well too, so that's great, and it's fun and it's interesting. So that's what I like from the organizational standpoint. From the other side of things, he, especially with the mathematics, I'm not much of a math person, but he exposes and talks about a lot of what I have observed taking math classes about what are some perceived inconsistencies that were never explained when I was learning math. And this is really important, I think, because it allows me to try to dispel and address these issues if I end up teaching mathematics, which I do, which you have to do it if you're doing science. The same thing in science. His reasons for why people believed certain things they did work out really well. One of his lessons was on Darwin, and he spoke about how, well, the issue isn't that Darwin went out to prove evolution or anything. Darwin just went out and made all these observations and was forced to come to his conclusion. I mean, here's a guy, Darwin, who was supposed to be an Anglican minister. I mean, he's not out to disprove God or anything like that. So anyway, there are countless examples of that. He spoke about Galileo and how the whole issue that people nowadays think of is, well, there was a scientist and the church was against him, and so it was church versus science. And Dr. Martinez spent a long time trying to make it very clear that that's not what the situation was. It was one scientist versus another scientist, and in that time, basically the educated people were in the church. And I think this helps a lot with understanding the science now, to how we got to the point where we're in now, and why, which is great, because then we can figure out where we're going to be going. So I think those are the strengths of this course. So one thing that I like about this that he points out, so just about every week, is that simply stating a fact and saying this is the way things are, it doesn't really help very much. It might help for test scores and that sort of thing, but it doesn't really help cultivate the mind, really. Because you, as he's pointed out several times, you really need to know the logic behind how people got to where they got. Otherwise, it's very difficult to go forth.
Well, I've never liked the history class. Like classes in history, I mean, I've been a math person, quote unquote, and I've always fallen asleep in history courses, and I'm just like, they're just boring, you know? And actually, we're actually talking about something that I guess that they've taught us. They really never showed us why or how it really worked. They just kind of goes, hey, this is this because, you know, A squared plus B squared equals C squared. That's the rule. And I guess learning more about the history and how it came about actually caught a lot of interest. I think that in a math class, a lot of students either are the math kids or they're another type of kid, you know, that reading or history or some other kid, and they lose interest in the class because it's not their subject. And I think adding that math into it or the history, putting them together is just a perfect way, in my opinion, of just catching everybody's interest in the class. So it's easier, I guess, to remember a subject instead of actually just trying to learn it or memorize things. And you attach that history to it. Plus, I enjoy math more now. I mean, I'm going through my classes and I'm like seeing the other side behind it because I read more about the history before now. I can actually want to understand it. Yes, it will help me with my teaching, I guess, in the future. Just even now, I'm taking classes where I have to teach my students, or elementaries or middle schools, and I'm going to help and do lessons in the semesters and incorporating different facts that intrigues the kids and actually gets their attention. I mean, kids like stuff like that. You know, I like stuff like that. I'm in class, I'm in college, I'm like, that's so cool, you know, and I love it. And it's just something that I think that if people know about, they'll find definitely interesting in class.